Hello everyone, and welcome back. Today we're going to be continuing our exploration of Markov processes and discuss what it means for a Markovian process to be absorbing. So let's first off go over a few very basic things associated with Markov processes that you definitely should know, just in case you aren't already familiar with the basics. So let's assume that we have a structure X, which is going to be a sequence of random variables xt that maps the set T to set S. And let's also assume that the probability distribution of these random variables, in particular the probability of variable xm plus 1, conditioned on x0, x1, all the way up to xn, can actually be uniquely determined by xn only. That is, the probability distribution of xn plus 1 only needs the information about xm, nothing before it. So if this stochastic process, x given by that sequence of random variables, satisfies this property, sometimes called the Markov property, then we say that x is a Markovian process, or Markovian stochastic process. Right? So that's what a Markov process is. And if we create a matrix, in particular, let's assume that P is a left or right stochastic matrix. So when we say it's a left stochastic matrix, that means the sum of the values in the column sum up to 1. All elements in the entire matrix belong to closed interval 0, 1. And if it's right, then it's a row sum of 1, not a column sum of 1. So if P is a stochastic matrix, then the structure constructed by pairing this stochastic matrix P with that sequence of random variables xt is sometimes called a Markov chain. A Markov chain. Right? So that's some of the terminology that you definitely should know or probably already know. So one very important property associated to Markovian processes is that if we let, for example, pk be the, and let's assume that our state space is discrete. So if that is the case, then we're going to have a probability mass function for random variables, in particular for xk. So the distribution for xk, x1, x2, x3, x0, xn need not be the same, right? Where k belongs to, of course, t. Then you can actually find one distribution from another. In particular, as long as you know the initial probability distribution, you can actually find the distribution of all other variables. Because keep in mind that the probability distribution of x1 actually only depends on the probability distribution of x0, and you can find it by multiplying the stochastic matrix P by P0. And recursively, you can find that the distribution for xk, which I'm going to represent by pk, can be found by iterating the matrix p to the power of k and then multiplying that by your initial distribution p0. Right? So that is the super property of Markov processes. So now let us introduce the first important definition that we need to work with. And there's so many applications of this type of matrix. So a stochastic matrix. So a stochastic matrix, and let's assume that the stochastic matrix's size n by m is called regular if there exists a number k belonging to the set 1, 2, 3, and also 0, all the way up to positive infinity, such that the matrix P raised to the power of k and the ijth element is greater than or equal to 0, in particular strictly greater than, not just greater than or equal to, and obviously that's less than or equal to 1. This identity has to be true for all ij in the set 1, 2, all the way up to m. So all the entries of the stochastic matrix need to be strictly positive in order for that matrix to be regular. So let's work out a few examples just to make sure we understand this definition. So let's assume that we have this matrix P, which is equal to 0.3, 0.7, 0.4, and 0.6. As we can clearly see, all entries of this matrix are strictly positive. So this is what I'm going to call trivially regular, because all you have to do is just look at that matrix and see that all of the entries are non-negative and also all strictly positive. Let's look at another matrix in particular the 2 by 2 matrix, P given by 0, 0.4, 1, and 0.6. And this matrix is trivially left stochastic. So it's not trivially regular because we do have a 0 entry in this matrix, but it doesn't mean if we exponentiate this matrix enough times that it's not eventually going to be trivially regular. So if it's not trivially regular, then you need to exponentiate this matrix. For example, we need to go to p squared. So we do 0, 0.4, 1, 0.6, and multiply that in the dot product fashion as usual by itself. And what you're going to get is the matrix 0.4, 0.6, 0.24, and 0.76. As you can see, all of the entries of this matrix are strictly positive. Therefore, since this is trivially regular, that means this original matrix is regular, right? So therefore, P is regular. Right. Now, a very interesting question you might be thinking, how many times do you need to exponentiate a matrix in order to trivially see that the original matrix is indeed regular, right? So that's where this next theorem comes into the play. So sometimes people will refer to this as the Perkins theorem for regular matrices, and it says the following. So suppose that P is an n by n left stochastic or even right stochastic matrix. Doesn't really matter here. So let's assume that P is a stochastic matrix. And let's define M to be equal to little m minus 1 squared plus 1. And again, little n is associated to the number of rows or number of columns of our stochastic matrix P. Then if P to the power of m, this capital M that is generated by the number of rows of our stochastic matrix P. So if this matrix P to the M is trivially regular, if it's trivially regular, then P is regular too. Right? So one can also show that M is the smallest natural number that you have to check in order for you to test trivial regularity. Right? So what exactly does this mean? So if we have a P that is of dimension n by n, what is the value of m that we would have to try? So we've already looked at 2, but if we do 2 minus 1 squared, that's going to be 1 squared plus 1, that's obviously going to be 2. So for our previous example, if we were to still have a 0 in our matrix, that means that since, p squared was not trivially regular, p cubed, p to the power 4 will not be also, right? So 2 is the largest we have to go for a 2 by 2. For a 3 by 3, we're going to have 3 minus 1, which is 2, squared is 4, plus 1 is 5. And then for n is equal to 4, we're going to have 4 minus 1, 3 squared is 9, plus 1 is 10, right? So we have to exponentiate by 10 times, which is definitely a lot, especially if you plan to do that by hand. So software definitely is your friend here, but technically speaking, you can continue in this fashion if you desire. Right, so let's just look at another example. Let's look at P, which is equal to the identity matrix 1, 0, 0, 1. So is this a regular matrix? So we already know that P to the power of n actually is just still going to be the identity matrix 1, 0, 0, 1. And that obviously is going to be true for all n in the set of natural numbers. So that means P obviously is not regular. But you don't have to try for all n. For associated to the Perkins theorem, we only have to try n is equal to 2. In order to see that, but as we can see, the identity matrix is not a regular stochastic matrix. So what exactly is so special about regular matrices and irregular matrices? Let's actually take a closer look at this identity matrix that is going to be represented in the transition matrix for some Markovian process. So obviously, since we have a 2 by 2, that means the cardinality of our state space is equal to 2, so let's call our states S1 and S2 without loss of generality. So we're going to have S1 and S2. So the probability of transitioning from S1 to S1 is 100%. The probability of transitioning from state 2 to state 2 is 100%. And the probability of transitioning from state 1 to state 2 is 0%, so P 1 is equal to 0. and the probability of transitioning from state 2 to state 1, i.e. P12, this is equal to 0 as well. So if you think about this from the directed graph perspective, we obviously have two isolated nodes in this picture, right? So if you have a matrix that is irregular, that is, it's always going to have at least 1 0 in the entry. So let's assume that P, actually let's assume that we have P, let's do PM, and M is that special Perkins number that we defined before, and this obviously is going to be equal to PM times our initial distribution for x0. Then if the ith, jth entry of this matrix is equal to 0, right? So that means that P is an irregular matrix, and that has to be for some I, j, n, 0, 1, 2. Actually, this is going to start at 1, 2, all the way up to n. So if this is true, then we will never be able to transition from where to where? Transition from Sj to Si. Some people will say that these states will never be able to communicate with one another, and that's kind of sad. As you've probably already figured out, graphs are very used to analyze Markov processes, in particular discrete Markov processes, right? So if you know any graph theory, you might have a little bit of an advantage in terms of analyzing these graphs, because these graphs are then equivalent to that of a Markov process, right? So let's assume that we have this transition diagram, or this directed graph, you could also view it as, in the following way. So we have three state spaces, S1, S2, and S3. Let's assume that S1 can transition to itself. Let's assume that S2 can transition to S1. Let's assume that S2 can transition to S3, S3 to S2, and let's assume that S3 can transition to itself. All other arrows that are not written in this diagram sometimes are assumed to be equal to 0. So since I didn't draw an arrow for 2, that means 2 cannot communicate with itself. We also see that 1 cannot communicate directly with S2, and we can clearly see that S1 does not communicate directly with S3, and S3 does not communicate directly with S1. Now there are a few conventions out there. Some people will write this equivalently as S1, S2, S3. Some people will write the arrows going this way, this way, this way, and that's all they will write, which sometimes is implied that every state can communicate with itself, but in some cases you must transition for whatever reason. For example, if you think about a one-dimensional random walk, you must either move to the left or to the right. You cannot stay still. But that only comes up to preference, so just make sure whatever directed graph that you are working with is the one intended for interpretation. But I'm just going to stay consistent, and I'm going to write these arrows in case it can connect with itself, and if you do not see the arrows, then that's practically what I'm intending here. All right? So if this is our particular Markov process, what would be an example of a stochastic matrix that represents this process, right? So obviously 1 communicates with itself, and 1 does not communicate directly with anyone else. So we're going to have 1, 0, 0 for state 1. And then for state 2, notice that state 2 can communicate with 1. It can communicate with S3, but it cannot communicate with itself, right? So for example, we can do 0.3, 0, and 0.7, and those numbers are just made up, but as long as they sum to 1, then everything is wonderful. And if we look at S3, obviously S3 communicates with itself, it communicates with S2, but it does not communicate with S1, therefore we're going to have 0 and then 2 non-zero entries, for example, 0.1 and 0.9. So that would be an example of a stochastic matrix that represents this Markov process via this transition diagram. So here we have a stochastic matrix, but it does have 0 entries in it. So one can ask, is this a regular matrix? Well, obviously it's not trivially regular, right? So what's the magic number m, our Perkins number? So that's going to be equal to 3 minus 1 squared plus 1, so it's going to be 2 squared plus 1, which is going to be equal to 5. So let's just jump to this exponential of the matrix just to see if it contains any zero entries. So if we do p to the power of 5, one can find this is going to be approximately equal to 1, 0, 0, 0.36, 0.06, 0.58, 0.11, 0.08, and 0.81, right? So as you can clearly see, these are still 0, and you probably shouldn't be surprised because regardless of how many times you iterate this process, 1 will never be able to communicate with those other entries. Because, once you get to 1, you're sort of stuck there, right? But as we clearly see, P5 does contain some zero entries, therefore P is not regular, right? So this state, S1 actually, is a special example of a state called an absorbing state. So let's provide a nice little explanation of what we're talking about, right? So if state I converges to S1 for our particular example, then, and let's assume that this is true for any I, then it stays at S1 forever, or at that point and every time thereafter, right? So if this is the case, then we call S1 an absorbing state of the process, All right, so what exactly is an absorbing state? Well, that's obviously an absorbing state. If it gets there, it stays there. So if it gets there and stays there, that means the associated column for that state has to contain 1 at that state index and 0 everywhere else, right? So what happens when all of the entries are sort of absorbed into some particular state? And keep in mind, you could have potentially more than one absorbing state. So the second definition is what we refer to as an absorbing Markov chain. Right, so let's suppose that Sj, let's assume that this belongs to S, be a state of a Markov chain. Let's assume this Markov chain is characterized by P and Xt. And let's assume that Pij is equal to 1. So the index of focus here is j. And let's assume that Pij is equal to 1. And obviously if Pij is equal to 1, then that means P, and keep in mind this is a stochastic matrix, P entry ij. This is going to imply that Pij is going to be equal to 0 for all I not equal to j. And this is true if I is equal to, actually no, we don't need to say that. Right? So if this is the case, then we call Sj an absorbing state of the Markov chain. So that's the formal presentation of it. And we can build on this, right? So a Markov chain is said to be an absorbing Markov chain. Is said to be an absorbing Markov chain if it satisfies two properties. The first property that it must satisfy is that there is at least one absorbing state. There must be at least one absorbing state in your Markov chain. And for all Sj in the state space of your Markov chain, let's call it C, with absorbing states, let's call it AK, where K, runs along some indexing set, then there exists a finite transition sequence such that if you have state Sj, and it goes to some other state, say S1, some other state S2, some other state S3, all the way down to some other state, say Sm-1, all the way down to Ak, where Ak is an absorbing state. So once it gets here, it stays here forever, right? So if it's at Ak, it's at Ak, and stays there, right? Right? And notice that if this is the case, we have 1, 2, 3, down to m-1, and then n, right? So this is where we're going for finite transition sequence, right? So if you have any state in your Markov chain, and all of them go to some absorbing state, then we say that that Markov chain is an absorbing Markov chain, right? So all of the entries in your Markov chain must converge to a absorbing state, right? So here's a nice little theorem that you might be able to prove on your own. It's actually very intuitive, and proving it probably isn't that much difficult either. So let's assume that C, that has stochastic matrix P, random variables xt, is a Markov chain. And let's assume that P is a regular transition matrix. Let's assume that P is a regular transition matrix. That means eventually the probability of going anywhere is possible because there's no zeros in that matrix. Then C is, so think about this. If this matrix P is regular, that means it contains no zero entries. So is it possible for C to be an absorbing chain if P is a regular matrix? You should be thinking no. So if P is regular, then C cannot be an absorbing chain. Absorbing chain. Right? And that explanation is practically just an informal proof of that particular theorem. All right? So here's just a couple questions that you probably can think about on your own, but I'll sort of walk through them with you, right? So does irregular P imply absorbing chain? Right? Because we clearly see that regular P implies non-absorbing chain, so does it go the other way around, right? So does a regular P imply absorbing chain? So think about that. You might want to pause your video and think about that. So let's consider the matrix P, which is equal to 1, 0, 0, 0, 0, 1, 0, 1, and 0. And keep in mind we're looking at this from the column perspective. So let's build a transition diagram for this. So what are we going to have? So we clearly have three states, S1, S2, and S3. So the probability that 1 goes to 1 is of probability 1, and that cannot go to the other. So I'm not going to draw any arrows here. And what do we have here? So this is state 2 going to state 3 is guaranteed to happen. So that's guaranteed to happen with probability 1. And 3 goes to 2 is guaranteed with probability 1, 2. So 2 and 3 sort of bounce back and forth with each other, and 1 sort of stays there where it is. Right? So you should be able to verify that this matrix here, P, is not regular. And some people will call that an irregular matrix, right? So does that mean that this is an absorbing chain? No. Well, obviously, we do have that S1 is an absorbing state. So we do have an absorbing state of S1, but S2 and S3 do not absorb into S1. And it doesn't absorb into any other state either, because S2 and S3 are not absorbing states either, right? So here we have an example of an irregular non-absorbing chain, right? So therefore C is not absorbing. But we do have an absorbing sub-chain in here. That is, if we sort of isolate this little piece of our Markov chain, just look at S1, that would be an absorbing subchain of our Markov chain. Right? So you can always do subchains of a chain if you desire. Right? So here's another question for you to think about. Can a Markov chain have more than one absorbing state and be an absorbing chain also. So more than one absorbing state and also an absorbing chain, right? So every state absorbs into something, and it has to have at least two absorbing states. So let's draw a little diagram. So let's actually do 4 just for excitement. So let's do S1, S2, S3, and S4. And let's draw our little directional arrows here. So let's assume that S1 can go to S2. Let's assume that S2 can go to S2. Let's assume that S1 can go to S1. Let's assume that S3 can go to S1. S1 to S3, S3 to S3, S3 to S4, S3 to S2. And okay, that should be okay. So let's look at our matrix P. So if we look at our stochastic matrix P, what would be an example of this? So if we look at 1, 1 can go to 1, 1 can go to 2, and 1 can go to 3, but 1 cannot go to 4. So we can do a 0.3, 0.2, 0.5, 0 distribution for that. If we look at S2, S2 is pretty much hanging out on its own and it does not communicate with anyone but itself. So we're going to have 0, 1, 0, 0 for state 2. And then we're looking at state 3. So state 3 can go to 2, 1, 4, and itself. So we can do a 0.1, 0.2, 0.3, 0.4 distribution for that. And if we look at lonely little S4, 3 is the only person that can communicate with it, but it doesn't communicate with anybody but itself. Right? So in that particular case, we're going to have 0, 0, 0, and 1. Right? So is this an absorbing chain? So are there any absorbing states? First off, well, we clearly see that state 2 is an absorbing state and state 4 is an absorbing state. Now we just need to make sure that all other states, in particular 1 and 3, can be absorbed into them. Right? So pretty much we need to make sure that S1 and S3 aren't sort of going back and forth with each other. Right? So we clearly see that S1 can get to S2, right? We clearly see that S1 can go to S2 via that path. So once it goes across that path, it's practically stuck there, right? So it can be absorbed into S2, but also notice that S1 can be absorbed into S4 if it changes to S3 and then into S4, right? So S1 can be absorbed into 2 and also to 4. It can be absorbed into both. And if we look at S3, S3 can be absorbed into S2 with one direct path. S3 can also be absorbed into S4 with one direct path. Therefore, everybody can be absorbed into the states. So let's state out our observations for this, right? So our S2 and our S4 are our absorbing states. These are our absorbing states. And S1, S2, and S3 can be absorbed into S2, and we have that S1, S3, and S4 can all be absorbed into S4, where S2 and S4 are our absorbing states. So since everyone is accounted for in our state space S, which has S1, 2, 3, and 4 in it, therefore we have that C, P, XT is an absorbing Markov chain. Right? So this is some of the basics that you definitely should know when it comes to Markov processes and what it means for a state to be absorbing and also what it means for a chain to be absorbing as well. Several applications of this and also several other classifications for states as well, which we'll get into a later video, but this is just an expository of this particular topic. Hope you enjoyed this video and I'll see you in the next one. Take care.